Imagine hearing a message from deep space, not just noise, but a structured transmission that proves we're not alone. NASA has decoded signals from 3 Atlas, an interstellar object that broke all the rules, and what it says could change everything we know. Don't miss a single discovery. Subscribe now. Our story begins not with a bang, but with a quiet digital whisper. In the vast, silent theatre of the cosmos, countless events unfold every second, most forever beyond our notice. But sometimes, a single flicker of light, caught by a robotic eye, can mark the beginning of a profound shift in our understanding of the universe. This is the story of one such flicker, an object that appeared without warning and challenged the very laws we thought governed our solar system. It was a silent alarm, a signal that something new had arrived. This is the story of how 3I Atlas first appeared. The night of the discovery was like any other on the summit of Haleakala, a dormant volcano on the Hawaiian island of Maui. Here, under some of the clearest skies on Earth, robotic telescopes stand guard, their unblinking eyes scanning the heavens. One of these guardians is the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Its mission is simple but vital: to scan the entire visible sky every few nights, looking for moving objects, specifically asteroids that could pose a threat to our planet. It is a sentinel, a planetary defense system designed to give us a precious few weeks of warning if a dangerous space rock were heading our way. On this particular night, the system was performing its duty flawlessly, its cameras taking rapid-fire images of the starfields, feeding a torrent of data into its processing computers. At precisely 2:43 Universal Time, a time standard used by scientists worldwide to coordinate observations, a new point of light entered the Atlas survey field. It was faint, unassuming, and to the naked eye indistinguishable from the tens of thousands of other stars in the frame. But the Atlas software is not a naked eye. It is an incredibly sophisticated program that compares new images with older ones, looking for anything that has moved. The system registered the new object and, following its protocol, gave it a temporary designation, TLS 2025 R2. This name was little more than a digital placeholder, a tag for a candidate that needed further review. In the world of automated sky surveys, thousands of such flags are generated. Most turn out to be cosmic rays hitting the camera sensor, glints from known satellites, or simply digital noise. This one, however, was different. It was a real object, moving with a purpose that the system was about to find deeply unsettling. The flag, TLS 2025 R2, was just one of many that night, but it triggered a specific and unusual response from the automated program. The software's primary job after spotting a moving object is to calculate its path, its orbit. It tries to fit the object's movement to the known rules of gravity within our solar system. Is it an asteroid from the main belt between Mars and Jupiter? Is it a comet from the distant Oort cloud, falling in towards the Sun on a long looping journey? The program runs through these possibilities, trying to find a mathematical curve that fits the data points. For TLS 2025 R2, the computer tried and failed. Again and again, the automated program halted its calculations because the object's motion simply didn't fit. It refused to conform to any known orbital path within our Sun's family. The problem was twofold. First, the object was moving too fast. Things that belong to our solar system are all bound by the Sun's immense gravity. Think of it like a cosmic merry-go-round. Everything on it, from the inner planets to the most distant comets, is spinning around the center. They can move faster or slower, but they are all stuck on the ride. This object was moving with such incredible velocity that it was clear it was not on the merry-go-round. It was like a bullet fired from far away, destined to streak through the ride and exit on the other side, never to return. Its speed was so high that the Sun's gravity could only bend its path slightly. It could never hope to capture it. The Sun's gravitational pull was not strong enough to hold on to something moving with that much energy. The second issue was the angle of its approach, its trajectory. Most objects in our solar system orbit on a relatively flat plane, known as the ecliptic. Imagine our solar system as a flat dinner plate, with the Sun in the middle and the planets orbiting in circles on the plate's surface. Most comets and asteroids follow this general rule, but TLS 2025 R2 was coming in at a steep angle, plunging down towards the plate from high above. This combination of extreme speed and a steep, unusual trajectory was a mathematical impossibility for anything born within our system. The automated program, faced with data it could not reconcile with its models, could only do one thing. It had to flag the object with a special, rarely used label, a label that carried with it a sense of cosmic otherness. The system labelled it unbound. This is a simple word, but in astronomy it has a profound meaning. An unbound object is one that is not gravitationally tied to our Sun. It is a traveller, a visitor from interstellar space, the vast emptiness between the stars. It was crossing our sky, passing through our cosmic neighbourhood, but it did not belong to us. It was a piece of another star system, a messenger from a distant, unknown place. For the computer system, this was simply a classification, a way to sort an anomaly. For the astronomers who would soon review the data, it was a signal that something incredibly rare was happening. Our solar system was being visited by an object from beyond. This classification was a quiet moment of revelation, delivered by a machine that had no concept of its significance. The label, Unbound, tells a story of a journey that is almost impossible to comprehend. It speaks of an object that has travelled for millions, perhaps even billions, of years through the cold, dark void between stars. It has drifted through interstellar clouds, survived the radiation of deep space, and journeyed across light years of emptiness, all before happening to pass through our tiny corner of the galaxy. Its path was not a loop or an ellipse, the comfortable repeating shapes of solar system objects. Its path was a hyperbola, an open-ended curve that meant it would come in, make a single pass by our Sun, and then continue on its journey back into the infinite darkness, never to be seen again. The discovery was a testament to the power of our modern survey systems, but it was also a profound accident. The Atlas system, as its name suggests, was built for defense. Its purpose is to map near-Earth threats, the asteroids and comets whose orbits cross our own. It is an inward-looking system, designed to protect our home. It was never intended to be an interstellar watchdog. The idea of finding visitors from other star systems was a fascinating but secondary possibility, a scientific curiosity rather than a primary mission objective. The fact that this system, designed to look for local dangers, was the one to catch this traveller from afar makes the discovery all the more remarkable. It was like a harbour patrol looking for small boats that might be a local hazard, suddenly spotting a vessel of a design never before seen on Earth, a ship that had clearly crossed an entire ocean to reach its shores. This unexpected nature of the detection highlights a critical point. We are only just beginning to get good at spotting these visitors. For most of human history, our view of the solar system was that of a closed, isolated family of planets. The idea that objects could travel between stars was theoretical, a concept that seemed plausible, but for which we had no direct evidence. The first confirmed interstellar object, a strange cigar-shaped visitor named Oumuamua, was only discovered in 2017. The second was a comet, Borisov, found in 2019. This new object, TLS 2025 R2, was only the third of its kind ever to be confirmed. How many others had passed by, unseen and unnoticed, throughout the centuries? This question would linger in the minds of the astronomers who first saw this data. The discovery was exciting, but it also carried a humbling realization of how much we were missing. The final element that made this initial detection so compelling was the object's persistence. In the world of automated astronomy, most alerts are fleeting. They are digital ghosts that appear in one image and are gone by the next. Thousands of potential candidates for new objects are flagged every night by surveys like Atlas. The vast majority of these are discarded by the software or by human reviewers. They vanish back into the noise from which they came, their brief moment of potential significance erased. They are phantoms in the machine, but this one was different. TLS 2025 R2 persisted. It appeared in the next image and the one after that. Its position changed with a steady, predictable motion. It was not a glitch, it was real. And as the software gathered more data points over the course of the night, its trajectory became clearer and simultaneously more bizarre. The curve of its path refused to settle into the familiar closed loop of a solar-bound orbit. The more data the system collected, the more certain it became that this object was on a one-way trip. Its path was a stark, open-ended line cutting through the familiar tapestry of our solar system. This persistence, this refusal to conform to our local rules, was the final confirmation that Atlas had stumbled upon something truly extraordinary. It was not just another rock, it was a traveller from another world. The silent alarm was now ringing, and the astronomical community was about to wake up to the news that they had a new and very mysterious visitor. But what if this wasn't just a mysterious rock? What if this interstellar visitor was not just passing by, but actively communicating? The initial discovery, made by a silent, automated system in the middle of the Pacific night, was just the first step. A single detection, no matter how strange, is never enough in science. It must be verified. The claim that an object has come from another star system is an extraordinary one, and it requires extraordinary evidence. So, as the Earth continued its rotation, bringing the dawn to Hawaii and darkness to observatories across the globe, a quiet, urgent process of confirmation began. What started as a digital flag on a server was about to become a tangible, tracked point of light, a confirmed unseen visitor whose presence would ripple through the astronomical community. The discovery of 3i Atlas was about to become official. By the time the sun's first rays touched the volcanic peaks of Maui, the work had already moved to other parts of the world. The coordinates of the strange object TLS 2025-R2 were automatically sent out to a network of professional and amateur astronomers. This is a standard procedure for any potentially interesting discovery. It is a call to arms for skywatchers, asking them to point their own telescopes at a specific patch of sky and confirm what the initial survey has seen. In observatories in Arizona, Chile, and Spain, astronomers interrupted their scheduled observations to slew their powerful telescopes towards the reported location. The race was on to get more data, to build a more complete picture of this fleeting visitor. The confirmations began to trickle in. Independent telescopes, operated by different teams in different countries, all found it. There, exactly where the Atlas data predicted it would be, was a faint, fuzzy smudge of light, moving steadily against the background of distant stars. Each new image added another piece to the puzzle, another dot on the graph of its trajectory. The faint trail was steady and unwavering, confirming that this was a single, solid object. With each new observation, the confidence grew. This was not a fluke. It was a real, physical thing that had entered our solar system. The initial lonely detection by Atlas was now a globally verified fact. With the object's existence confirmed, the next question was simple: what is it? The first possibility to rule out is always the most mundane. Could it be human-made space debris? There are thousands of pieces of junk orbiting our planet, from old rocket stages to defunct satellites. Sometimes, a piece of this debris can be pushed into an unusual orbit, making it appear in unexpected places. However, this was quickly ruled out. The object's trajectory did not originate from Earth's orbit. Furthermore, its speed was far too great. No piece of our own technology could achieve such a velocity and trajectory without a massive and very obvious rocket engine. It was not one of ours. The second possibility was that it was a known object, perhaps a long-lost asteroid or comet that had been rediscovered. Astronomers checked their extensive catalogues, which list every known object in the solar system. There was no match. This was something new. The final and most telling piece of evidence was its speed. As more data points were collected, the calculation of its velocity became more and more precise. The number that emerged was staggering, nearly 30 kilometers per second, or over 67,000 miles per hour. To put that in perspective, that is fast enough to travel from New York to Los Angeles in under 3 minutes. This is a speed that simply cannot be achieved by any object naturally orbiting our Sun at that distance. It possessed too much energy. This incredible velocity was the final, irrefutable proof of its origin. It had to have come from interstellar space. With its interstellar nature confirmed beyond any reasonable doubt, the object needed a formal name and an official announcement. This process, however, was not one of flashy press conferences or bold headlines. The world of astronomy often moves with a quiet, deliberate pace. The information was sent to the Minor Planet Center, or MPC, a global organization responsible for collecting data and calculating orbits for all small bodies in the solar system. The MPC is the official scorekeeper of the cosmos. Based at the Harvard-Smithsonian Center for Astrophysics, it is their job to verify new discoveries and share the information with the scientific community. The MPC issued an internal bulletin, a dry technical document filled with numbers and celestial coordinates. There was no fanfare. The announcement was just a few lines of text, distributed electronically to observatories and researchers around the world. It was a simple notice, a quiet statement of fact. Our solar system had a visitor from beyond. For the astronomers, reading this bulletin, it was a moment of quiet excitement. But for the rest of the world, there was nothing. No news alerts, no breaking stories. The arrival of a messenger from another star system went almost completely unnoticed by the public. It was a secret known only to the people who watched the skies. The bulletin also contained the object's new, official name, 3I Atlas. The name is a code that tells a story. The I stands for interstellar, confirming its origin. The 3 signifies that it is the third such object ever discovered, and Atlas honours the survey telescope that first spotted it. With this designation, the object was no longer a temporary candidate, TLS 2025 R2. It was now a formally recognised celestial body, a new entry in the catalogues of human knowledge. Yet this formal recognition came with a subtle but persistent sense of unease. The unease stemmed from a simple, humbling question. If we had only just found this one, and the 2 before it, how many more had we missed? Our ability to scan the entire sky with high-powered automated telescopes is a very recent development. For all of human history before the last decade, these interstellar visitors could have been passing through our system completely undetected. The discovery of 3I Atlas was a triumph of technology, but it was also a stark reminder of our previous blindness. It felt as though we had spent our entire lives in a house, believing we were alone, only to suddenly realise that visitors had been walking through the hallways all along. We just never had the tools to see them. This thought was both thrilling and unsettling for the scientific community. So, as the world turned, it did so as if nothing new had entered it. Billions of people went about their daily lives, completely unaware that an object from another star was currently hurtling through our cosmic backyard. In university departments and research institutions, astronomers read the MPC bulletin between sips of coffee, filed the information, and planned their next observations. They were excited, certainly, but it was a measured professional excitement. The initial shock of the discovery had passed, and now the hard work of science had to begin. The true nature of 3I Atlas was still a complete mystery. It was a faint point of light, a set of orbital numbers on a screen. The story of what it was made of, and why it was behaving so strangely, had yet to be written. The quiet notice from the Minor Planet Center had done its job. The existence of 3I Atlas was no longer a secret held by a handful of observatories. It was now public knowledge within the global astronomical community. But knowing an object exists and understanding it are two very different things. The initial data had provided its path and its speed, but it revealed nothing about its physical nature. Was it a comet? An asteroid? Something else entirely? To answer these questions, astronomers needed more than just a few dots on a map. They needed to collect its light, to analyse it, to wring every last secret out of the faint photons that had travelled for eons across interstellar space. This began a frantic new phase in the story of 3I Atlas, a desperate race against time. Scientists found themselves chasing a ghost. The confirmation of 3I Atlas as an interstellar visitor immediately triggered a race against the clock. The object was on a hyperbolic trajectory, a path that would bring it swinging around the sun before flinging it back out into deep space. This meant that astronomers had a very limited window of opportunity to study it. Every hour that passed, the object moved deeper into the sun's glare from our perspective on Earth. Observing objects close to the sun is incredibly difficult. The overwhelming brightness of our own star washes out the faint light of distant objects, making them impossible to see. It is like trying to spot a firefly next to a searchlight. Soon 3I Atlas would be lost in the daytime sky, completely hidden from our view. This created an atmosphere of extreme urgency in observatories around the world. There was no time to waste. Every clear night was a precious gift. A bout of bad weather, a technical glitch with a telescope, or any other delay could mean losing the object forever. Teams of astronomers scrambled to book time on the world's most powerful telescopes. Schedules were rearranged, planned observations were postponed, all to focus on this one, fleeting target. The object was moving fast, and the scientific community had to move even faster. It was a chase, but the quarry was millions of miles away, and the finish line was the blinding light of the sun. The window for observation was closing day by day. In this high-stakes environment, photons became a form of currency. A photon is a single particle of light, the smallest possible quantity of it. The light from 3i Atlas was incredibly faint. It was an object likely no more than a few hundred meters across, and it was already tens of millions of miles away. The number of photons arriving at Earth from it each second was minuscule. To study it, astronomers needed to collect as many of these precious particles as they could. Observatories became like photon banks, with researchers trying to collect what they could before the opportunity was gone forever. Every second of exposure time with a large telescope was like a deposit, adding to a fragile collection of data. The work was painstaking and often frustrating. Astronomers would wait until the very last moments before sunrise, when the sky was as dark as it could be, to try and capture a few final images. They would push their equipment to the absolute limits of its sensitivity. Even with the world's best telescopes, the object was barely visible. On the raw images, it was just a few faint pixels, almost lost in the background noise of the camera sensor. The challenge was to gather enough of these faint signals to build a clear picture. It required immense patience and technical skill. Each observation was a small victory in the ongoing race against the sun. The initial images that came back were, to be honest, thin and featureless. They showed a small, unresolved point of light. To a non-expert, the pictures would have been completely underwhelming. There was no grand, majestic comet tail, no detailed surface features. It looked like a tiny speck of cosmic dust. But to the trained eye of a scientist, even this simple image held clues. The first and most important step was to stack the data. This is a technique where astronomers take many short exposure images and digitally combine them. This process amplifies the faint signal of the object while averaging out the random background noise. It is like taking 100 faint whispers and combining them to create a single, clear word. As the data from different observatories was collected and stacked, a clearer though still blurry picture of 3i Atlas began to emerge. The speck of dust sharpened into a more defined object. While it was still too small and distant to see any surface details, scientists could now begin to measure its properties more accurately. They could get a better estimate of its size, its brightness, and most importantly, how that brightness changed over time. It was in these subtle changes that the first real mystery of 3i Atlas would be found. The object was beginning to hint that it was not just a simple, boring rock. The most intriguing discovery from these early images was a subtle, rhythmic pulse in the object's brightness. As astronomers watched 3i Atlas move across the sky, they noticed that its brightness was not constant. It was changing in a regular, repeating pattern. This is not unusual for asteroids or comets. Most space rocks are irregularly shaped, more like a potato than a perfect sphere. As they tumble through space, they expose different sides to us. A broad, flat side will reflect more sunlight and appear brighter, while a narrow end will reflect less and appear dimmer. By measuring these changes in brightness over time, astronomers can determine how fast an object is spinning. But there was something odd about the light curve of 3i Atlas. The pulsing was incredibly regular and smooth. Most asteroids and comets tumble chaotically. They spin on multiple axes at once like a badly thrown football. This results in a complex and messy light curve, with lots of irregular peaks and dips. The light curve of 3i Atlas, however, was clean and simple. It suggested that the object was not tumbling. Instead, it was rotating smoothly around a single stable axis. Furthermore, there was a slight asymmetry in its brightness. It seemed to have one side or one edge that was consistently brighter than the rest. This hinted that the object wasn't just a randomly shaped lump. It suggested a more structured form, something with a degree of symmetry. This was the first piece of evidence that 3i Atlas might not be a broken, natural piece of rock. Its steady, rhythmic spin was a quiet clue that we were looking at something far more unusual. The pursuit of 3i Atlas was a perfect example of modern collaborative science. Data flowed freely between institutions. Teams from around the world worked together, sharing their observations and analysis in real time. It was a global effort, united by a common goal, to understand this mysterious visitor before it vanished from our sight. The pressure was immense, but so was the excitement. Every new piece of data, no matter how small, was a victory. It was a testament to human curiosity and our relentless drive to explore the unknown. Even as the object faded, the determination of the scientific community only grew stronger. As astronomers continued to track the faint light of 3i Atlas, they were doing more than just taking pictures. They were meticulously plotting its position, measuring its exact location in the sky at precise moments in time. This is the science of astrometry, and it is the foundation upon which our understanding of the solar system is built. By gathering enough of these data points, scientists can calculate an object's orbit with incredible precision. They can predict where it has been and where it is going, but as they applied this science to 3i Atlas, they found that its path was unruly. The object was refusing to follow the rules. Gravity alone didn't fully explain its motion. The initial orbital measurements for 3i Atlas were consistent with what one would expect from an interstellar object. Its path was a clear hyperbola, a testament to its high speed and external origin. This basic picture was clear. However, as more and more data poured in from observatories around the world, the details of that orbit started to get fuzzy. The small, subtle aspects of its movement did not quite add up. It was like listening to a piece of music where one instrument is slightly out of tune. The overall melody is there, but something is just not right. The first clue came from the photometric curve, the graph of its changing brightness. As we noted, the brightness of 3i Atlas was changing with a very regular, smooth rhythm. This rhythm tells scientists its spin rate, the time it takes to complete one full rotation. For 3i Atlas, this period was remarkably stable. The strange part was that the brightness changes did not perfectly match what was expected for its spin rate. There was a small but persistent discrepancy. The way its brightness waxed and waned hinted at a shape and a motion that were slightly at odds with each other. It was a subtle inconsistency, the kind that might be dismissed as an error in measurement. But as different teams confirmed the same data, it became clear that the discrepancy was real. The object's light was telling a more complicated story than a simple spinning rock. This led astronomers to consider the most common explanation for such behavior in comets. Comets are often described as dirty snowballs. They are mixtures of ice, rock, and dust. As a comet gets closer to the Sun, the ice on its surface heats up and turns directly into gas, a process called sublimation. This release of gas creates jets that shoot out from the comet's surface. These jets act like tiny natural rocket engines. They can push on the comet, causing it to change its spin or even alter its orbital path. This is a well-understood phenomenon. So the natural assumption was that 3i Atlas must be a comet, and its strange behavior was being caused by these gas jets. To test this idea, astronomers turned to spectroscopy. This is a technique where they split the light from an object into its component colours, like a rainbow. By looking at this spectrum, they can see the chemical fingerprints of the materials the object is made of. If 3i Atlas were venting gas, its spectrum should show bright bands corresponding to the gases being released, such as water vapour or cyanide, which are common in comets. So they pointed their spectrographs at the faint visitor, expecting to see the telltale signs of a gassy halo. What they found was complete silence. The spectral readings were flat. There was no sign of any gas, no dust, no coma. 3i Atlas was not shedding any visible material. This was a major puzzle. It had the motion of a comet being pushed by gas jets, but none of the visible evidence. With the comet explanation looking unlikely, the focus shifted back to the object's orbit. The orbital calculations were refined again and again, using the latest, most precise measurements of its position. And that is when the most baffling discovery of all was confirmed. The calculations revealed a small but steady deviation from its predicted path. 3i Atlas was not moving exactly where gravity said it should. It was accelerating, but only by a tiny amount. This non-gravitational acceleration meant some other force, besides the pull of the Sun and planets, was acting on it. The force was not random. It was a constant, gentle push, always in the same direction away from the Sun. The first explanation scientists considered was solar radiation pressure. Sunlight, even though it has no mass, carries momentum. When photons of light hit an object, they exert a tiny push. For a very small, lightweight, or large and thin object, this pressure can be enough to slightly alter its orbit over time. Think of it like the wind pushing a sailboat. The pressure is gentle but constant, and it can steer the boat. Could 3i Atlas be a cosmic sailboat being pushed by the light of the Sun? The problem was that for solar radiation pressure to account for the observed acceleration, the object would have to be incredibly lightweight and have a very large surface area, something like a sheet of foil just a few meters thick. While not impossible, this would be a very strange shape for a natural object. This strange combination of features, smooth acceleration, no visible gas, and a shape inferred from its light curve, was eerily familiar. It rang a bell in the minds of astronomers who had studied the first interstellar visitor, Oumuamua, discovered 8 years earlier. Oumuamua, which means scout in Hawaiian, had baffled scientists with the exact same set of characteristics. It too had shown a slight non-gravitational acceleration with no visible outgassing. Scientists had struggled to explain Oumuamua, proposing everything from a fluffy porous rock to a cosmic dust bunny. The most controversial theory, put forward by Harvard astronomer Avi Loeb, was that Oumuamua was an artifact of an extraterrestrial civilization, perhaps a solar sail or a probe. Now, with 3i Atlas, it seemed that history was repeating itself. This second interstellar object was exhibiting the same physics-defying behaviour that had made its predecessor so famous and so controversial. The unruly orbit of 3i Atlas was not just a puzzle, it was a pattern, and it was a pattern that was becoming increasingly difficult to explain with conventional science. With the most obvious explanations for the object's strange acceleration failing, astronomers hoped that a deeper look into its composition would provide the answer. The key to understanding any celestial object lies in its light. By carefully analysing the light that reflects off its surface, scientists can unlock the secrets of what it is made of. This is the science of spectroscopy, and it is one of the most powerful tools in modern astronomy. The community turned to this tool with great anticipation, hoping it would solve the riddle of 3i Atlas. They expected the light to tell them a story. Instead, they were met with a frustrating and defiant silence. The riddle in the light was that the spectrum refused to speak. Astronomers were hopeful that spectroscopy would be the key to unlocking the mystery. The process works by taking the faint light from a distant object and passing it through an instrument called a spectrograph. This device acts like a very precise prism, splitting the light into its full rainbow of colours. But it does more than just create a pretty picture. When light bounces off a surface, certain colours, or wavelengths, are absorbed by the elements and molecules present in that surface. This leaves dark or bright lines in the spectrum which act like a chemical barcode. By reading this barcode, scientists can determine with amazing accuracy what an object is made of. For example, the spectrum of a typical asteroid will show the signatures of rock and metal, while a comet's spectrum will reveal the presence of various ices and organic compounds. The expectation was that the spectrum of 3i Atlas would reveal its true nature. If it were a rocky asteroid, even one from another star system, its spectrum should show the absorption lines of silicates and other minerals. If it were a dormant comet, with ice hidden just beneath its surface, there should still be some faint signature of water or other frozen materials. Every known type of object in our solar system has a characteristic spectral signature. So, the world's most powerful telescopes were pointed at 3i Atlas, their spectrographs ready to capture and dissect its faint ancient light. The data was collected over many hours, slowly building up a signal strong enough to analyse. When the first graphs were produced, the astronomers who saw them were baffled. The graphs were nearly blank. The reflected light from 3i Atlas, when spread out into its component colours, produced a quiet, featureless slope. There were no prominent absorption lines, no bright emission bands, no chemical fingerprints of any kind. The spectrum was almost perfectly flat with a slight reddish tint, but otherwise it was completely mute. It was as if the object was made of something that absorbed all wavelengths of light almost equally, a property that is very unusual in natural materials. It was a chemical barcode with no lines on it. This was not what anyone had expected. The silence of the spectrum was a direct contradiction to the object's behaviour. As we have seen, 3i Atlas was accelerating as if it were a comet venting gas, but ordinary comets have very distinct and recognisable spectra. As they approach the Sun, the sublimating ices release gases like cyanogen and carbon compounds. These gases glow when excited by solar radiation, producing very strong, bright emission bands in the spectrum. The spectrum of a typical active comet is full of these features. It is a loud, clear signal of its composition. The spectrum of 3i Atlas, by contrast, showed none of this. Its silence was a form of defiance. It was behaving like a comet but refusing to show the evidence. Confronted with this puzzle, the researchers did what good scientists always do. They tried again. Perhaps the initial exposures were too short. Maybe the signal was just too weak to pick out the subtle features. So they dedicated even more precious telescope time to observing 3-eye Atlas. They used different instruments, different filters, and longer exposure times, all in an attempt to force the object to reveal its secrets. They stacked image upon image, spectrum upon spectrum, hoping that a hidden signal would emerge from the noise. But the result was always the same. The spectrum stayed stubbornly, unnervingly mute. There was no hint of gas jets, no sign of a dusty coma. The light coming from 3-eye Atlas was clean, simple reflected sunlight with no additional information. This led to a profound contradiction that sat at the heart of the mystery. How could an object be a comet that refuses to vent? It was a paradox. The non-gravitational acceleration it was exhibiting was its most prominent feature, the thing that made it so strange and interesting. This acceleration was the primary reason to suspect it was a comet, but the total lack of a coma or any spectral evidence of outgassing was an equally strong piece of evidence that it was not a comet. The two most important pieces of data about the object were in direct opposition to each other. They could not both be true, at least not within our current understanding of how comets work. This forced scientists to start thinking about more exotic possibilities. Could the object be made of something that vents a gas that is invisible to our instruments? Some proposed that 3-eye Atlas could be a chunk of solid hydrogen or solid nitrogen, a kind of interstellar iceberg. These substances would turn to gas at the extremely low temperatures of deep space, and the resulting gas would be transparent and very difficult to detect. This was an intriguing idea, but it came with its own problems. A chunk of frozen hydrogen, for example, would be very fragile and would likely not survive a journey of millions of years through interstellar space. It would have evaporated long ago. The idea seemed to solve one problem while creating several others. The silent spectrum of 3-eye Atlas was perhaps the most frustrating aspect of the entire investigation. The object was right there, a tangible thing that we could track and measure. And yet, when we asked it the most basic question, "What are you made of?" it gave us no answer. Its light, the very medium that should have carried its story across the cosmos to our telescopes, arrived as a blank page. This lack of information was, in itself, a powerful piece of information. It suggested that we were dealing with something that did not fit into our neat categories of asteroids and comets. It implied that something unknown was at play, or perhaps that we were encountering a form of physics or a type of material that we had not yet understood. The riddle in the light was a stark reminder that the universe is not obligated to make sense to us. The steady accumulation of strange and contradictory data from 3-eye Atlas did not lead to a clearer understanding of the object. Instead of uniting the scientific community around a single theory, the evidence had the opposite effect. It created deep divisions, fracturing researchers into different camps, each with its own interpretation of the baffling data. The object became a cosmic Rorschach test. What one scientist saw as a natural anomaly, another saw as a profound mystery that hinted at something more. The consensus that usually forms around new discoveries began to crack, as scientists found themselves divided over the evidence. On one side of the debate were the traditionalists, the cautious voices who urged patience and restraint. This group argued that while the data was certainly unusual, it was not yet time to jump to extraordinary conclusions. Science, they pointed out, is filled with puzzles that seem inexplicable at first, only to be solved later by a new discovery or a better understanding of the physics involved. They insisted that there must be a natural explanation for the behaviour of 3-eye Atlas, even if we had not found it yet. Perhaps it was a new type of comet, one that vented a gas we couldn't detect. Or maybe its strange acceleration was caused by a combination of factors, like its shape and the way it was heated by the sun. This side urged for more data. They argued that the object was still very far away and difficult to observe. The measurements had uncertainties, and it was possible that these small errors were creating a misleading picture. Their message was simple: let's not get ahead of ourselves. The history of science is littered with examples of supposed discoveries that turned out to be nothing more than measurement errors or misunderstood data. For this group, the burden of proof was on those who claimed 3-eye Atlas was something truly exotic. Until every single possible natural explanation had been exhausted, it was unscientific to consider more radical ideas. They represented the voice of scientific skepticism, a crucial component of the process. On the other side of the divide was a smaller but equally vocal group of scientists. These researchers looked at the same evidence: the non-gravitational acceleration, the lack of a coma, the strange light curve, the featureless spectrum, and saw not just an anomaly but a repeating pattern. They pointed out that we had seen this exact set of bizarre characteristics before. With Oumuamua, to have one such object appear in our solar system could be dismissed as a fluke, a one-in-a-billion natural curiosity. But to have two of them, showing the same suite of physics-defying behaviours, in less than a decade strained the idea of coincidence to its breaking point. This group argued that dismissing 3I Atlas as just another weirder rock was a failure of imagination. They contended that when a pattern repeats, it demands a new explanation. The chances of two independent natural objects from different star systems both happening to be a new undiscovered type of hydrogen iceberg or nitrogen comet seemed incredibly small. For these scientists, the evidence was pointing towards something more profound. They did not necessarily claim it was aliens, but they were adamant that the mystery should be taken seriously and that unconventional ideas should be untheatable. They saw the cautious approach of the other camp as being overly conservative, a refusal to engage with the truly strange nature of the data. The debate largely took place out of the public eye, in the emails, academic papers, and private conversations between scientists. A private memo began to circulate among researchers, written by a prominent astronomer. The memo laid out, point by point, the stark similarities between the path of 3I Atlas and that of Oumuamua. It highlighted the statistical improbability of two such objects appearing so close together in time. This memo, which was leaked to a few science journalists, sparked a series of cautious statements from major observatories and space agencies. They acknowledged the similarities but reiterated their official position that natural explanations were still being investigated. The divide was becoming more public. Behind the scenes, the language being used was even more pointed. In emails exchanged between researchers at NASA and the European Space Agency, ESA, the debate was frank and sometimes heated. While their public statements maintained a confident belief in natural explanations, their private correspondence revealed a deep sense of puzzlement and division. Researchers debated the merits of the solar sail hypothesis, the idea that the objects were being pushed by sunlight acting on an incredibly thin artificial structure. In the silences between their formal replies, in the questions they asked each other late at night, the word propulsion began to appear. It was never stated as a fact, but as a question. Could this non-gravitational acceleration be a form of deliberate, controlled propulsion? This division in the scientific community is a healthy and necessary part of the scientific process. It is through debate, argument, and the challenging of ideas that we move closer to the truth. However, the case of 3I Atlas was putting this process under immense strain. The two sides were not just disagreeing on the interpretation of the data, they were disagreeing on the fundamental nature of the object itself. One side saw a natural, if unusual, phenomenon. The other saw evidence of something that could potentially rewrite our understanding of the universe and our place in it. The cracks in the consensus were growing wider with each new piece of data that came in. The object was not getting any easier to explain. If anything, the mystery was deepening. The public, largely unaware of this intense behind-the-scenes debate, continued with their lives. But within the halls of astronomy, the arrival of 3I Atlas had ignited a firestorm of controversy. The object was forcing scientists to confront the limits of their knowledge and to ask uncomfortable questions about what might be possible in the vast universe beyond our small solar system. The evidence was on the table, but what it meant was anyone's guess. The community was split, and the mystery of 3I Atlas was far from being solved. As 3I Atlas continued its journey through our solar system, it grew ever fainter. The window for observation from ground-based telescopes was closing rapidly. The object was now so dim and so close to the sun's glare that even the largest telescopes on Earth were struggling to get a clear view. It seemed as though the mystery might slip away, unsolved, as the object disappeared back into the interstellar void. But humanity has eyes in places other than the surface of our planet. In a remarkable display of ingenuity and quick thinking, engineers and scientists repurposed two powerful instruments already in space, turning them towards this fleeting target. The Hubble Space Telescope and an orbiter around Mars named Cassini joined the hunt. By the second week of observations, the situation for Earth-based astronomers had become critical. 3i Atlas was now so faint that it was at the very edge of what our best telescopes could detect. The faint trickle of photons that had travelled across interstellar space was being drowned out by the light of our own atmosphere and the encroaching dawn. The ghost was fading. For many observatories, the chase was over. They had collected all the data they could, and now they could only watch as their target disappeared from view. It was a frustrating moment. The object was still displaying its strange, unexplained acceleration, but we were losing our ability to track it with the precision needed to understand it. But where Earth-based telescopes failed, space-based telescopes could succeed. Above the distorting effects of our atmosphere, telescopes in orbit have a much clearer view of the cosmos. The most famous of these is the Hubble Space Telescope. However, getting time on Hubble is incredibly difficult and competitive. Scientists must submit proposals months or even years in advance. There was no time for that. But the case of 3i Atlas was so compelling that the Space Telescope Science Institute, which operates Hubble, agreed to grant emergency director's discretionary time. Hubble was about to be pointed at the interstellar visitor. However, an even more unlikely hero was about to enter the story from an orbit hundreds of millions of miles away. The European Space Agency's ExoMars Trace Gas Orbiter, or TGO, was circling the planet Mars on a completely unrelated mission. Its primary job is to study the Martian atmosphere, looking for trace gases like methane that could be a sign of geological or even biological activity. It carries a suite of sensitive instruments, including a powerful camera system called the Color and Stereo Surface Imaging System, or CASSIS. The CASSIS camera is designed to take incredibly detailed, high-resolution color images of the Martian surface, mapping its canyons, craters, and polar ice caps. It was never ever intended to be used for astronomy. It was a geologist's tool, not an astronomer's. However, a clever team of engineers realized that CASSIS, with its powerful optics, might just be able to spot the faint light of 3i Atlas. The plan was audacious and technically challenging. The orbiter was not designed to track moving objects in the distant sky. Its systems are built to look down at the planet directly below it. So, the engineers had to improvise. They could not simply point the camera at 3i Atlas and take a long exposure image. The object would move, and the spacecraft itself was orbiting Mars, so the image would be a useless smear. Instead, they came up with a brilliant workaround. They would take a series of very short sequential images, creating an intentional blur. The idea was to capture the object's motion as a faint streak across the camera's sensor. By analysing the shape and brightness of this streak, they hoped to extract information about the object itself. It was a long shot. The object was at the absolute limit of what the camera could detect, but the team worked around the clock, writing new software and reprogramming the orbiter to perform this unlikely observation. In an amazing feat of interplanetary engineering, the instructions were sent across the void to Mars. The TGO, a probe designed to study a planet, turned its camera outwards to the stars and hunted for an interstellar ghost. The gamble paid off. When the data came back from Mars, the team processed the images, and there it was, a faint, blurry streak, exactly where 3i Atlas was predicted to be. The blur itself was a treasure trove of information. The engineers noticed something subtle but significant. The streak was not uniform, it had a structure. The leading edge of the blur, the part corresponding to the front of the object as it moved, was consistently sharper and slightly brighter than the trailing edge. This was not an artifact of the camera or the motion, it was a real feature of the object. This suggested that 3i Atlas was not a uniform tumbling potato. It hinted at symmetry, a defined front and back, or a very specific and stable rotation. A few days later, the Hubble Space Telescope, the most powerful optical telescope ever built, confirmed the CASSIS findings. Hubble was also forced to use special techniques to observe the faint moving target. Like the Mars orbiter, it took a series of rapid images. The data was crystal clear. Hubble's superior vision showed the same rhythmic pulse in brightness that ground-based telescopes had seen, but with much greater detail. More importantly, it confirmed the same asymmetry seen by CASSIS. Across consecutive exposures, the object's brightness profile showed a consistent repeating pattern. The faint visitor was not just a rock, it had a structure, and it was moving in a way that was becoming increasingly difficult to explain as a natural phenomenon. The eyes in the sky had not only found the ghost, they had seen its shape. The images from the Cassis camera on the Mars orbiter and the Hubble Space Telescope were, to the public, completely unimpressive. They were just blurry streaks and faint dots. There was none of the cosmic beauty one usually associates with pictures from space. But for the imaging analysts who pored over this data, these unremarkable blurs contained a stunning revelation. Hidden within the pixels was the proof that 3i Atlas was rotating in a way that was highly unusual for a natural space rock. The blurs revealed a perfect, unnatural spin, a discovery that would deepen the mystery and push the debate about the object's origins into even more radical territory. The imaging analysts began by comparing the blurs from Cassis pixel by pixel. The technique was painstaking. They took the faint streak of light and measured its brightness at every point along its length. What they found was a consistent and repeating pattern. The brightness was not uniform. It shifted from the leading end of the blur to the trailing end in a very specific way. This pattern was not random noise. It was a clear signal that was embedded in the data. It was the signature of the object's rotation, captured in the blur of its motion across the camera sensor. This pattern repeated at incredibly regular intervals. As the scientists analysed the series of images taken by both Cassis and Hubble, they saw the same brightness profile appear again and again, like a repeating beat in a piece of music. The pattern was too uniform, too precise, to be dismissed as a random fluke or an instrumental error. The object was behaving with a clockwork regularity. This was the first major clue. Natural objects in space, especially small ones like comets and asteroids, are rarely so perfect. They are typically scarred by billions of years of collisions and uneven heating, causing them to tumble and wobble in complex ways. The motion of 3i Atlas was by contrast clean and orderly. The data all pointed to one inescapable conclusion. 3i Atlas was rotating on a fixed, stable axis. Instead of tumbling chaotically through space like most comets and asteroids, it was spinning smoothly, like a perfectly balanced top. Imagine throwing a random lumpy rock. It will flip and tumble in a messy, unpredictable way. Now imagine spinning a carefully crafted gyroscope. It will rotate smoothly and stably around a single axis. The motion of 3i Atlas was like the gyroscope, not the rock. This kind of stable rotation, known as principal axis rotation, is not impossible for a natural object, but it is less common, especially for an object that has travelled through the turbulent environment of interstellar space. What made this discovery even more startling was that the object's rotation stayed constant. Its spin rate did not change over the entire period of observation. It remained perfectly smooth and deliberate. This was particularly strange given that the object was also experiencing a non-gravitational acceleration. If this acceleration were caused by jets of gas erupting from its surface, as in a typical comet, those jets should have had a noticeable effect on its spin. They would act like small thrusters, pushing and torquing the object, causing its rotation to speed up, slow down, or wobble. But 3i Atlas was being pushed by an invisible force, and yet its spin remained perfectly undisturbed. It was behaving as if it were perfectly balanced, even while being subjected to an external force at interstellar speeds. This combination of factors was deeply puzzling. A stable, principal axis rotation suggests an object that is symmetrical and has a uniform density. The constant, unperturbed spin, even while accelerating, suggests that the force acting on it was being applied perfectly through its centre of mass, or that the object had some internal mechanism to stabilise itself. Neither of these scenarios is easy to explain for a natural object. It would be like finding a log floating down a river that is not only spinning perfectly like a lathe, but is also gently accelerating forward without any visible means of propulsion, and without its spin being affected by the current. The images, while visually unremarkable to the public, told the scientists a quiet but profound truth. The perfect controlled motion of 3i Atlas suggested a lack of natural chaos. It hinted at a level of order and stability that was difficult to reconcile with a random chunk of rock and ice that had been wandering the galaxy for millions of years. This discovery added another thick layer to the mystery. The object was not only accelerating without a trace of gas, but it was also spinning with the grace and precision of a man-made machine. While no one was ready to say it out loud in an official capacity, the thought was now unavoidable. Its perfect motion seemed to suggest an intention, or at least a level of internal structure that was not consistent with a natural origin. The blurry pictures from Hubble and a Mars probe had revealed a ghost that moved with an unnatural grace. The story of 3i Atlas was becoming a story of constant revision. Every new piece of data seemed to complicate the picture rather than clarify it. This was most apparent in the ongoing effort to pin down its exact orbital path. In the world of celestial mechanics, calculating an orbit is a process of refinement. You start with a rough estimate and then use new observations to make it more and more accurate. But with 3i Atlas, this process broke down. The initial orbital solutions lasted barely a week before needing major corrections. Each new measurement forced an update, pushing the model further and further from a simple explanation, and leading to a growing sense of unease among the scientists tracking it. This was the era of rewriting the rules, a time of constant orbital corrections and a growing mystery. The first orbital solution, the mathematical description of the object's path, was published by the Minor Planet Center shortly after 3i Atlas was discovered. It was based on the first few nights of observation. For a typical asteroid or comet, this initial orbit is usually quite good. New observations will tweak it slightly, refining the numbers to be more precise, but the basic path remains the same. With 3i Atlas, this was not the case. The first orbit was a poor predictor of its future position. Just a few days later, the object was not quite where the model said it should be. The deviation was small, but it was significant. A new, corrected orbit had to be calculated and published. This became a repeating pattern. Every new measurement that came in from telescopes around the world forced another update to the orbit. The databases that astronomers rely on had to constantly rewrite the history of 3i Atlas. An orbit that was considered accurate on Monday was obsolete by Friday. This was highly unusual. It meant that the object's motion was more complex than the models could easily account for. It was not following a simple, predictable path governed solely by the gravity of the Sun. The mysterious non-gravitational acceleration was making it incredibly difficult to forecast its movement accurately. The Minor Planet Center, the official body in charge of these things, had to issue 5 separate circulars in just a few weeks, each one correcting the trajectory, brightness, and rotation period data for 3i Atlas. Each new circular was an admission that the previous one had been wrong. This was not the fault of the astronomers or their calculations. The math was correct. The problem was the object itself. It was simply refusing to behave. The constant revisions were a sign of a deep and persistent puzzle. The more we learned about 3i Atlas, the less we seemed to understand it. This created a strange paradox. The more data we collected, and the more accurate our measurements of the object's position became, the less stable and predictable the story of 3i Atlas looked. Usually more data leads to more certainty. In this case, more data led to more confusion. The problem was the small but consistent deviations from its forecast path. The object was always bending its trajectory in the same direction, away from the Sun, and the amount of this deviation was not changing. It was a constant, gentle push. This meant that whatever force was acting on 3i Atlas, it was continuous and controlled. This constant refusal to obey its forecast path was deeply unsettling for the celestial mechanicians, the experts who calculate orbits. Their entire field is built on the predictable, elegant laws of gravity laid down by Isaac Newton and refined by Albert Einstein. These laws are universal. They work for planets, asteroids, comets, and stars. They are the bedrock of our understanding of the cosmos. But 3i Atlas seemed to be ignoring them. It was as if the object was listening to a different set of rules, suggesting that something beyond the simple physics of gravity and sunlight was at play. The struggle to model the orbit of 3i Atlas can be compared to trying to predict the path of a car that has a driver. If you see a car rolling down a hill with no one in it, you can use the laws of physics to predict its path very accurately. You can account for gravity, friction, and the slope of the hill, but if there is a driver in the car, all of your predictions will be wrong. The driver can hit the brakes, turn the wheel, or press the accelerator. The car is no longer a passive object subject only to natural forces. It is under intelligent control. The constant corrections needed for the orbit of 3i Atlas felt like trying to predict the path of that car with a driver. The object appeared to be making its own small, continuous course corrections. This was, of course, a radical thought, but the data was pushing some scientists in that direction. The object's refusal to obey its forecast was not just a technical problem. It was a profound hint that we were missing a fundamental piece of the puzzle. As 3i Atlas moved further from the Sun and further from Earth, it grew progressively fainter. The frantic race to observe it had now turned into a patient, challenging vigil. Capturing its diminishing light required extreme effort and the world's most sensitive instruments. The object was becoming a whisper in the sky. Yet, even as its signal faded, the core mysteries remained. Its strange, controlled movement persisted, and its light, though faint, continued to tell a story of profound anomaly. The fading echo of 3i Atlas was a quiet but constant reminder of the unanswered questions it had brought into our solar system. At this stage in its journey, 3i Atlas was faint but still traceable. It was no longer a target for amateur astronomers or smaller observatories. Only the largest, most powerful professional telescopes could still hope to see it. Each new attempt to image the object became a major undertaking. It required long exposure times, sometimes lasting for hours. The timing had to be perfect, catching the object in the darkest part of the night, in the brief window between moonset and sunrise. Even then, the object was almost invisible on the raw camera frames. It was a ghost, a handful of photons scattered across a few pixels, barely distinguishable from the random noise of the detector. The process of confirming a detection was painstaking. Scientists would take dozens of long-exposure images and then use sophisticated software to stack them. Only after this intense digital processing would the faint trace of 3i Atlas emerge from the background. What was once a crisp, clear streak of light in the early discovery images had now thinned to a soft, uncertain trace. The object was pushing the very limits of what our technology could study. Each new data point was a hard-won victory, a testament to the persistence of the astronomers who refused to let the visitor disappear without giving up all its secrets. The faintness of the object made studying its properties incredibly difficult. Measuring its brightness, its colour, and its spin became a major challenge. The signal was so weak that the uncertainties in the measurements were large. Despite these difficulties, the core elements of the mystery remained unchanged. The object was still on a trajectory that showed a clear, non-gravitational acceleration. Even as it moved into the colder, outer reaches of the solar system further from the Sun, the gentle push continued. This was a crucial piece of information. If the push were caused by the sublimation of ice, it should have decreased as the object moved away from the Sun's heat. The fact that it remained constant was yet another argument against the comet hypothesis. Despite the diminishing signal, the object continued to move exactly where its updated orbital models predicted it would. The constant revisions to its path had finally resulted in a model that could accurately account for the mysterious extra acceleration. This model was complex and unconventional, but it worked. The ability to predict the object's position, even as it faded, was a triumph of the astronomers' skill and persistence. It showed that while they did not understand the cause of the acceleration, they could now accurately describe its effect. The object was behaving in a consistent, predictable way, even if that behaviour was itself completely strange. The faint light that our telescopes managed to collect still carried the same frustratingly uninformative message. The spectrum remained flat and featureless. The light still reflected cleanly, with no hint of dust or gas surrounding the object. Even as it receded from the Sun, 3i Atlas refused to reveal its composition. Its surface, whatever it was made of, had a uniform, slightly reddish colour, but beyond that it was a complete enigma. The consistency of its physical properties, even as its environment changed, was another piece of the puzzle. It was a solid, inert object that was somehow propelling itself through space with no visible means of propulsion. The most compelling aspect of these late-stage observations was the persistence of its controlled movement. The data from its light curve, though now much harder to obtain, was still consistent with a smooth, stable rotation around a single axis. The object was not tumbling, it was spinning with the same clockwork precision it had shown when it was closer and brighter. The combination of a steady, unexplained acceleration and a perfectly stable, unperturbed spin remained the central, baffling paradox of 3i Atlas. Even as it faded into a whisper, its behaviour continued to shout that it was not a natural object. The consistency of its controlled movement, even as it prepared to leave our solar system forever, was perhaps the most profound clue of all. It was a final, quiet testament to its deeply mysterious nature. The appearance of 3I Atlas, a second interstellar object exhibiting a bizarre set of physics-defying behaviours, forced the scientific community to look back and re-examine the case of its predecessor, Oumuamua. The discovery in 2017 had been a singular event, a cosmic oddity that had been debated and then largely filed away as an unsolved mystery. But now, with a second, strikingly similar object on the scene, the questions were being asked with a new urgency. Was this a cosmic coincidence? Or were we witnessing a pattern, a repeated signal that demanded a new, and perhaps uncomfortable explanation? The Oumuamua connection was impossible to ignore. The most significant and baffling similarity between 3I Atlas and Oumuamua was their motion. Both objects displayed a clear, non-gravitational acceleration. They were both being pushed by a force other than the gravity of the Sun and planets. This is the single most anomalous feature that sets them apart from every other known object in the solar system, with the exception of active comets. Yet, in both cases, this acceleration came without any of the visible signs of cometary activity. There were no gas jets, no dust, no coma. This was the core paradox for both objects. It was a direct contradiction, a behaviour that our current understanding of celestial mechanics cannot easily explain. The idea that both objects were a new type of comet, perhaps venting a transparent gas like hydrogen, was proposed in both cases. However, as we have seen, this explanation is fraught with problems. A solid hydrogen iceberg is unlikely to survive an interstellar journey. To have two such objects arrive in our solar system within a few years of each other would be an extraordinary coincidence. The universe would have to be filled with these strange, invisible comets for us to encounter two of them so quickly. While not impossible, it begins to stretch the bounds of probability. The repeated observation of acceleration without outgassing was a pattern that strongly suggested we were missing something fundamental. The second stark comparison was in their rotation. Both Oumuamua and 3I Atlas displayed unusual stable rotation. While Oumuamua's exact shape was debated, its light curve suggested it was highly elongated and rotating in a way that was more orderly than a chaotic tumble. 3I Atlas took this a step further, with its data pointing to a remarkably smooth and stable spin around a single axis. This is in sharp contrast to most natural comets and asteroids, which are irregularly shaped and tend to tumble in a complex manner. The orderly, controlled rotation of both objects hinted at a degree of structural integrity and symmetry that is not typical for a random piece of space debris. The third parallel was the mystery of their composition. The spectral analysis of both objects provided little to no useful information. Oumuamua, like 3I Atlas, had a featureless reddish spectrum. It gave no clear chemical signature, leaving scientists to guess at what it was made of. This lack of information from two separate interstellar visitors is, in itself, a significant finding. It suggests that they may be made of a material or have a surface coating that is not common among the objects in our own solar system. Their refusal to show us their chemical barcodes was a shared trait, another piece of the repeating pattern. The repeated breaking of the rules of physics by two interstellar visitors in less than a decade was putting a severe strain on the idea of coincidence. In science, a single anomaly can often be dismissed as a fluke or an outlier, but when the same set of anomalies appears a second time, it becomes a pattern, and a pattern requires an explanation. The scientific community was now faced with a choice. They could either assume that there is a vast, previously unknown population of strange natural objects in the galaxy that behave in this specific counterintuitive way, or they had to start seriously considering the alternative, that these objects are not natural at all. This brings us to the fundamental question at the heart of the 3I Atlas mystery. Are we witnessing a new, but entirely natural cosmic phenomenon, or are we seeing something else entirely? The natural phenomenon explanation would require a major revision of our understanding of comets and the formation of small bodies in other star systems. It would mean that objects like hydrogen icebergs are not only possible but common throughout the galaxy. It is a plausible, though unproven, hypothesis. The something else category is, of course, far more speculative. It includes the possibility that these objects are artifacts of extraterrestrial technology. This is the hypothesis famously championed by Avi Loeb for Oumuamua, the idea that the object was a probe, a solar sail, or some other piece of technology from another civilization. With the arrival of 3i Atlas, this controversial idea was suddenly much harder to dismiss. The pattern of evidence was forcing even the most skeptical scientists to admit that the question was worth asking. The Oumuamua connection had transformed the debate from a discussion about one weird rock into a profound inquiry about our place in the cosmos. With a growing consensus that 3i Atlas could not be easily explained by our current models of the universe, the scientific community entered a phase of intense and creative speculation. The central mystery remained. What could account for all the observed facts? The object was accelerating without visible propulsion, it was spinning with perfect stability, and it had a featureless spectrum. No single, simple theory seemed to fit. This led to a deep dive into the various explanations, from the exotic to the truly radical, all while emphasizing the frustrating lack of a satisfying scientific conclusion. The unanswered questions about 3i Atlas were pushing the boundaries of known physics. Scientists first tried to find an answer within the realm of known, if rare, natural phenomena. The leading theory for a while was the idea of a nitrogen iceberg. The theory goes that in the outer reaches of a distant star system, on a planet similar to Pluto, a massive impact could have ejected a large chunk of frozen nitrogen into interstellar space. A nitrogen iceberg would be solid and stable enough to survive the journey. As it approached our Sun, the frozen nitrogen would sublimate, turning into a transparent gas that would be invisible to our spectrographs. This would create the non-gravitational acceleration without a visible coma. It was an elegant and clever theory that seemed to explain the main paradox. However, the nitrogen iceberg theory had its own problems. While it explained the acceleration and the lack of a coma, it did not easily explain the object's perfect, stable rotation. The outgassing of nitrogen would likely happen from sun-facing hotspots on the surface, creating uneven jets that should have caused the object to tumble or wobble. The clockwork spin of 3i Atlas was a strong piece of evidence against this idea. Furthermore, calculations showed that a nitrogen iceberg would have to be of a very specific shape and density to produce the observed acceleration, making it a rather contrived explanation. While plausible, it left crucial questions unanswered. Another theory proposed that 3i Atlas had a carbon-rich crust that had been hardened and darkened by eons of exposure to cosmic radiation. This could explain its dark, reddish colour and its featureless spectrum. Underneath this crust, there might be volatile ices. As the object was heated by the sun, these ices could vent through tiny invisible cracks in the crust, producing the acceleration. This was another attempt to reconcile the object's behaviour with that of a comet. But again, it struggled to explain the stability of the rotation. It also begged the question of why the venting gas would be completely invisible and why it wouldn't kick up any dust from the dark crust. No single natural explanation seemed to perfectly fit all the observed data points. Every theory solved one part of the puzzle, while making another part even more confusing. The combination of non-gravitational force without visible exhaust, perfect rotation, and spectral silence remained the major unsolved puzzle. The problem was not that there were no possible explanations. The problem was that every explanation came with a major contradiction. It was like a detective story where none of the suspects' alibis checked out completely. The data was clear, but the story it told was incoherent within the known rules of astrophysics. This led to a growing realization that either our understanding of comets and the physics of the interstellar medium needed a major rewrite, or we were looking at something entirely unprecedented. This highlights the struggle of the scientific method when faced with a true anomaly. Science is built on a foundation of skepticism. The core principle is that extraordinary claims require extraordinary evidence. The claim that 3i Atlas might be artificial is about as extraordinary as it gets. Therefore, the scientific community is rightly hesitant to even consider it, until all natural possibilities have been exhausted. However, the method also requires us to follow the evidence wherever it leads. When a pattern of anomalies repeats, as it did with Oumuamua and 3i Atlas, it becomes increasingly unscientific to ignore it, or to keep trying to force it into existing, ill-fitting boxes. The unease was palpable. The situation forced a difficult question. At what point does the refusal to consider an extraordinary explanation become an unscientific bias in itself? If an object displays multiple characteristics that are hard to explain naturally, but are easy to explain by artificial design, when is it appropriate to consider the artificial explanation as a valid scientific hypothesis? There is no easy answer to this question. For now, the official consensus remained that 3I Atlas was a natural object of a type we do not yet understand. But behind this official stance, the debate raged on, and the mystery of the interstellar visitor continued to deepen. The unanswered questions were piling up, and the universe was offering no easy answers. For weeks, the data flowing back from 3I Atlas was treated as a collection of physical measurements. Astronomers analysed its position, its brightness, its spin, and its spectrum. They saw anomalies and paradoxes, but they viewed them through the lens of physics and celestial mechanics. The breakthrough came when a small group of data scientists and radio astronomers decided to look at the problem from a completely different angle. They began to wonder if the noise in the data wasn't noise at all. This shift in perspective from physics to information was the key that unlocked the final shocking chapter of the story. This was the moment of decoding the silence, the breakthrough in telemetry. For weeks, the telemetry, the stream of data describing the object's state, was seen as a complex set of numbers with strange, unexplained variations. The non-gravitational acceleration, the stable spin, the photometric light curve, these were all treated as separate physical puzzles to be solved. The noise in these measurements, the tiny rapid fluctuations, were dismissed as instrumental errors or the effects of the interstellar medium. It was standard scientific practice to try to filter out this noise to get a clearer signal of the underlying physics. But one team decided to do the opposite. They decided to look at the noise itself. They observed that the noise wasn't truly random. Random noise, like the static on an old television, has a specific mathematical signature. The fluctuations in the data from 3I Atlas did not fit this signature. They had a subtle, rhythmic quality. There was a structure to the randomness, a deliberate pattern hidden beneath the surface. It was as if someone were whispering very quietly underneath a loud conversation. If you weren't listening for it, you would miss it entirely, but once you knew it was there, you could start to pick it out. The team began to apply techniques from cryptography and signal processing to the telemetry data, treating it not as a physical measurement, but as a potential message. As they looked at the data in this new light, other things started to click into place. The equations that described the object's motion, particularly the non-gravitational acceleration, began to look less like simple physics and more like coordination. The constant, gentle push was not just a force, it was a series of tiny, controlled adjustments. The object wasn't just drifting and being pushed by a natural force, it was actively managing its trajectory. The motion was more akin to a spacecraft making minute course corrections than a comet being pushed by random jets of gas. The mathematics of its movement started to resemble the mathematics of guidance and control systems. The perfectly balanced, constant rotation also took on a new meaning. In physics, a tumbling object is in a state of high entropy, or disorder. A stable, spinning object is in a state of low entropy, or high order. The object's refusal to tumble, its insistence on maintaining a perfect, stable spin, suggested the presence of an internal mechanism designed to maintain that order. It could be an internal gyroscope or a sophisticated momentum control system. This was no longer just a hint of symmetry, it was evidence of active stabilization. The object was not just a passive piece of rock, it was a machine designed to maintain a specific orientation and stability as it traveled through space. This shift in perspective was the crucial breakthrough. By recognizing the possibility of structure in the anomalies, the team had found a new way to interpret the data. The silence of the spectrum was not a lack of information. It was a deliberate choice to be inert and non-reactive. The non-gravitational acceleration was not a mysterious physical force, it was a controlled, low-energy propulsion system. The perfect spin was not a coincidence of shape and density, it was a deliberate stabilization mechanism. The object's behavior was not a violation of physics, it was a demonstration of engineering. The team realized they were not observing a natural object, they were tracking a probe. The noise in the telemetry was not noise at all, it was the probe's own internal data stream, a faint signal leaking out, carrying information about its status and its mission. The silence was about to be decoded, the culmination of weeks of frantic work and audacious thinking, arrived not in a flash of light, but in a quiet, sterile conference room at NASA headquarters. The world was about to change forever. The team that had reanalyzed the telemetry from 3i Atlas had succeeded beyond their wildest dreams. They had not only confirmed that the patterns in the data were artificial, but they had also managed to decode them. The object was not silent. It had been broadcasting a message all along. The revelation of what 3 Atlas finally said to humanity would mark a definitive turning point in our history, a moment when we learned, with absolute certainty, that we are not alone. NASA officials, in a press conference broadcast around the globe, made the stunning announcement. They confirmed that they had successfully decoded coherent transmissions from the interstellar object 3i Atlas. The statement was delivered with a somber and careful tone, but its content was world-shattering. The noise that had been detected in the object's telemetry was, in fact, a highly complex structured signal. It was a message, deliberately encoded and broadcast with a startling level of efficiency. The era of speculation was over. The proof was now undeniable. The content of the transmissions provided clear, undeniable proof of an artificial origin. The decoded signal was not a simple hello. It was a rich, dense stream of information. The initial breakthrough came when the team recognized that the signal was structured around a set of universal mathematical constants, like pi and the fine structure constant. This is a common trope in science fiction, the idea of using math as a universal language, but in this case, it was real. The use of these fundamental constants of the universe as a basis for communication was the first unambiguous sign that the message was composed by an intelligent mind. Initial interpretations of the message suggested that it was a form of beacon or a directional signal. A large portion of the decoded data consisted of what appeared to be a detailed map. It was not a map of our solar system, but a three-dimensional map of our local galactic neighborhood. It pinpointed the location of our Sun relative to several other nearby stars, including some that are not easily visible from Earth. The map was dynamic, showing the movement of stars over millions of years. It was a navigational chart of stunning complexity and precision. It was as if the object was saying, "You are here." But the most profound part of the message was not the map. It was the mathematical and physical information embedded within it. The decoded information included mathematical sequences and patterns that were far beyond anything expected from a natural object. It contained elegant proofs of mathematical theorems that human mathematicians had not yet solved. It included descriptions of physical principles that hinted at a technology far beyond our own, including what appeared to be a working theory of how to manipulate space-time on a microscopic level. It was not just a message, it was a primer, a condensed encyclopedia of advanced science. What it said was this: we were not the intended recipients of the message. The probe, which the message referred to as a wayfinder, was part of a network of similar objects that formed a galactic-scale positioning system. They were ancient, autonomous, and their primary function was to maintain and update a navigational grid for a civilization that had either long since vanished or had transcended to a state we could not comprehend. The message was a routine status update, a broadcast between machines, which we had accidentally intercepted. This realization was both humbling and terrifying. We were not just not alone, we were so insignificant that our presence was not even a consideration for the beings who had built this network. We were like ants in a house who had just overheard the faint hum of the electrical wiring. The message from 3i Atlas fundamentally altered humanity's perception of life beyond Earth and the vastness of the cosmos. It was not a message of greeting or of warning. It was a message of profound cosmic indifference. It revealed a universe that was not empty, but was filled with the ancient working technology of a civilization so advanced that we were beneath their notice. The silence had been broken, not by a conversation, but by an accidental eavesdropping on the workings of the gods. The decoding of the message from 3i Atlas was not an end, but a beginning. It marked the start of a new chapter in the story of our species, a chapter we were never supposed to witness. The confirmation of an active artificial interstellar object, a piece of advanced technology operating within our own solar system, had profound and immediate implications for every aspect of human life. From science and religion to politics and our long-term future, everything was now viewed through the lens of this new, terrifying, and awe-inspiring reality. the implications for Earth and beyond were staggering. The discovery redefined the story of humanity. For our entire existence, we have operated under one of two assumptions. Either we are alone in the universe, or we are waiting for a moment of first contact. The message from 3i Atlas revealed a third, far more complex reality. We are not alone, but we are also not a part of the conversation. Our place in the universe was not one of special creation or lonely solitude, but one of profound cosmic obscurity. We were a primitive, emerging intelligence in a galaxy that was already ancient and filled with the works of our superiors. This realization forced a re-evaluation of our most fundamental beliefs about our own importance. The discovery also provided a stunning vindication for the scientists who had noted the object's anomalous behavior. It confirmed that physics was not lying. The non-gravitational acceleration was not a new, unknown force of nature. It was an engine. The perfect spin was not a coincidence. It was a stabilization system. An artificial intelligence was actively maneuvering the probe, making tiny, precise course corrections. The paradoxes that had baffled astronomers were not paradoxes at all. They were the signatures of technology. The object was not breaking the laws of physics, it was using them in ways we had not yet mastered. This event moved human history into a chapter we were never meant to witness. The knowledge that we had intercepted a private communication between parts of a galactic-scale network was a heavy burden. It forced a global re-evaluation of our priorities. The petty squabbles and conflicts that had defined so much of our history seemed utterly insignificant in the face of this new reality. The focus of humanity began to shift outwards, towards the stars, with a new sense of urgency and purpose. We were no longer just exploring space out of curiosity. We were now trying to understand our place in a universe we now knew to be inhabited. The implications for space exploration, technology, and potential future contact are immense. The decoded message, with its hints of advanced physics and mathematics, became a new Rosetta Stone. Scientists and engineers around the world began the monumental task of trying to understand and perhaps even replicate the technology it described. It sparked a new space race, not between nations, but for our entire species, a race to catch up, to learn, to grow, and to perhaps one day be worthy of joining the galactic conversation. The question of future contact became the single most important issue facing humanity. Do we try to signal our presence? Do we remain hidden, hoping to learn more before we reveal ourselves? The debate was fierce and global. Ultimately, this chapter prompts a deep reflection on what it means to be a sentient species in a universe now known to be populated by others. The message from 3i Atlas was a humbling and powerful lesson. It taught us that the universe is far older, stranger, and more complex than we had ever imagined. It showed us that we are at the very beginning of our journey, but it also gave us a new sense of hope and a unified purpose. We were no longer just humans on planet Earth. We were Earthlings, the newest members of a cosmic community, with an infinite and challenging future ahead of us. The story of 3i Atlas was over, but the story of humanity's new chapter had just begun. What are your thoughts on the message from 3i Atlas? Share your theories in the comments below, and let's explore this new chapter in human history together.